There are a lot of them, elementary counting problems. In the first two chapters, we have explained how to use the pigeonhole principle and the method of mathematical induction to draw conclusions from certain numbers. However, to find those numbers is not always easy. It is high time that we learned some fundamental counting techniques. Permutations. Let us assume that n people arrive at a dentist's office at the same time. The dentist will treat them one by one, so they must first decide the order in which they will be served. How many different orders are possible? This problem, that is arranging different objects linearly, is so omnipresent in combinatorics that we will have a number of for both the arrangements and the number of arrangements. However, we are going to answer the question first. Certainly, there are n choices for the person who will indulge in dental pleasures first. How many choices are there for the person who goes second? There are only n-1 choices, as the person who went first will not go second, but everybody else can. The crucial observation now is that for each of the n choices for the patient to be seen first, we have n-1 choices for the patient who will be second. Therefore, we have n times n-1 ways to select these two patients. If you do not believe this, try it out with 4 patients called A, B, C, and D. And you will see that there are indeed 12 ways the first 2 lucky patients can be chosen. We can then proceed in a similar manner. We have n-2 choices for the patient to be seen third, as the first 2 patients no longer need to be seen. Then we have n-3 choices for the patient to be seen fourth, and so on. 2 choices for the patient to be seen next to last, and only 1 choice, the remaining frightened patient, to be seen last. Therefore, the number of orders in which the patients can sit down in the dentist's chair is n times n-1 times n-2 and so on times 2 times 1. Definition 3.1. The arrangement of different objects into a linear order using each object exactly once is called a permutation of these objects. The numbers n times n-1 times n-2 and so on times 2 times 1 of all permutations of n objects is called n factorial and is denoted by n factorial. We note that by convention, 0 factorial is equals to 1. If you really want to know why we choose 0 factorial to be 1 and not say 0, here is an answer. Assume there are n people in a room and n people in another room. How many ways are there for people in the first room to find a line and the people in the second room to form a line? The answer is, of course, n factorial times n factorial, as any line in the first room is possible with any line in the second room. Now look at the special case of n equals to 0. Then people in the second room can still form n factorial different lines. Therefore, if we want our answer n factorial times n factorial to be correct in this singular case too, we must choose 0 factorial equals to 1. You will soon see that there are plenty of other situations that show that 0 factorial equals to 1 is the good definition. So we have just proved the following basic theorem. Theorem 3.2. The number of all permutations of an n-element set is n factorial. The number n factorial is quite essential in combinatorial enumeration, as you will see throughout this book. You may wonder how large this number is in terms of n. This question can be answered at various levels of precision. All answers that are at least somewhat precise require advanced calculus. Here we will just mention without proof that n factorial is approximately equals to the square root of 2 pi n times n divided by e, then to the exponential n. The symbol n factorial, which is approximately equals to z of n psi, means that the limitations of n factorial divided by z of n when n goes to infinity is equals to 1. Relation 3.1 is called Stirling's formula, and we will use it in several later chapters. Example 3.3. How many different three-color flags can we construct using colors red, white, and green? Solution. By Theorem 3.2, the answer is 3 factorial equals to 3 times 2 times 1 equals to 6. It is easy to convince ourselves that this is indeed correct by listing all 6 flags: RWG, RGWW, RG, WGR, and GWR and GRW. The simplicity of the answer to the previous question was due to several factors. We used each of our objects exactly once. The order of the objects mattered, and the objects were all different. In the rest of this section, we will study problems without one or more of these simplifying factors. Example 3.4. A gardener has 5 red flowers, 3 yellow flowers, and 2 white flowers to plant in a row. In how many different ways can she do that? This problem differs from the previous one in only one aspect. The objects are not all different. The collection of the 5 red, 3 yellow, and 2 white flowers is often called a multiset. A linear order that contains all the elements of a multiset exactly once is called a multiset permutation. How many permutations does our multiset have? We are going to answer this question by reducing it to the previous one, in which all objects were different. Assume our gardener plants her flowers in a row in any of different ways. Then stick labels, say numbers 1 through 5 for the red flowers, 1 through 3 for the yellow ones, and 1 through 2 for the white ones, to her flowers so that she can distinguish them. Now she has 10 different flowers, and therefore the row of flowers she has just finished working on can look in 10 factorial different ways. We have to tell how many of these arrangements differ only because of these labels. The 5 red flowers could be given 5 different labels in 5 factorial different ways. The 3 yellow flowers could be given 3 different labels in 3 factorial different ways. The 2 white flowers could be given 2 different labels in 2 factorial different ways. Moreover, the labeling of flowers of different colors can be done independently of each other. Therefore, the labeling of all 10 flowers can be done in 5 factorial times 3 factorial times 2 factorial different ways once the flowers are planted in any of 8 different ways. Therefore, 8 times 5 factorial times 3 factorial times 2 factorial is equals to 10 factorial. Or, in other words, A is equals to 10 factorial divided by the multiplications of 5 factorial, 3 factorial, and 2 factorial, which is equals to 2520. This arrangement can easily be generalized to a general theorem. However, we will need a greater level of abstraction in our notations to achieve that. This is because we will take general variables for the number of objects, but also for the number of different kinds of objects. In other words, instead of saying that we have 5 red flowers, 3 yellow flowers, and 2 white flowers, we will allow flowers of k different colors, and we will say that there are A1 flowers of the first color, A2 flowers of the second color, A3 flowers of the third color, and so on. We will complete the set of these conditions by saying that we have AK flowers of color K or AK flowers of the kth color. This is a long set of conditions. So some shorter way of expressing it would certainly make it less painful. We will achieve this by saying that we have AI flowers of color I for all I which is in K braces. Instead of saying that we plant our flowers in a line, we will often say that we linearly order our objects. Now we are in a position to state our general theorem. Theorem 3.5. Let n, k, a1, a2, and so on to ak be non-negative integers satisfying a1 plus a2 and so on plus ak equals to n. Consider a multiset of n objects in which ai objects are of type I for all I which is in k braces. Then the number of ways to linearly order these objects is n factorial divided by a1 factorial times a2 factorial and so on times ak factorial. Proof: this is a generalization of example 3.4, and the same idea of proof works here. The reader should work out the details.